Hey everybody, it's Dr. J, and today we are talking about heteronuclear diatomic molecules. Let's talk chemistry. So far everybody, in the previous videos, we've only talked about homonuclear diatomic molecules. But now let's talk about some heteronuclear. So basically this is where we have different atoms, all right? And what you're going to notice is a lot of compounds have different atoms. So adjacent elements are going to be most similar, right? So we can use those same molecular orbitals because they're adjacent to each other. All right, so essentially we can use the molecular orbitals as we do in homonuclear diatomics. All right, only for adjacent. So basically they're right by each other. It's a little bit different, the farther distance they are from each other. Now, the more electron negative an atom is, the lower in energy the orbitals are going to be. So when it comes to molecular orbitals, as far as how you're drawing them, your the electron negativity is going to impact it. So basically, we look at this example down here: nitrogen and oxygen, nitrogen monoxide forming together. In this case, we got our valence electrons and our 2s2 and 2p for nitrogen, so we got 5 in total. And oxygen, we know is going to have 6, 4 in the 2p, 2 in the 2s. So when it comes to actually this little hint here, the more electron negative the atom is, the lower in energy, right? Oxygen is a little bit more electron negative, so the orbitals are a little bit lower. Okay, so that's what we see here. So they're not equal in this case with the energy level. So lower energy atomic orbitals are going to contribute more to the bonding molecular orbitals, and higher energy atomic orbitals will give more to the antibody. All right, so we see this up here. All right, so like I said, this one is a little bit complicated, but it's still the same overall. For instance, right, we got our 2 here, so we're still going to be forming, right, our 1, 2 in our sigma 2s orbital, our 2 in our sigma 2s star orbital. In this case, we're taking in total 1, 2, 3, 4, 5, 6, 4, 7. So we have our 7 here. In this case, we're going to have an unpaired electron in our top pi star 2p orbital there. When it comes to elements being far apart, you got to do it a little bit different in this case. So they're very different because they're going to have very different energies. So because of this, we're actually going to have like a new type of molecular orbital that will be built. For instance, if we look at hydrogen and fluorine coming together, fluorine super electron negative. It's actually the most electron negative atom, and compare that to hydrogen, right? Not that electron negative. Okay. So when it comes to this, we have what we call non-bonding orbitals. These non-bonding orbitals are basically going to essentially have the same energy in the molecule as they do in an atomic system. So they're not actually giving, right, anything to the bond order. So for example, right, this is an example of HF. We got that 1 electron in my 1s orbital. In this case, we see the 4 in my 2p. So in this case, we're going to form our antibonding and our molecular, right, our bonding, sigma here, sigma star, 2 from here, 1 from our hydrogen. But now those extra electrons will be going to non-bonding orbitals instead of the antibonding because of those far apart energy levels. Okay, so that's all we're going to talk about with non-bonding orbitals. All right, non-bonding orbitals, it gets crazy, y'all. Like I said, there's a whole class dedicated to this, and this is just an intro level. So let's just do an example together, right? Let's draw the molecular diagram of Cn anion, right? In this case, I'm going to ask you what's the bond order, and once we find a bond order, is it going to be paramagnetic or diamagnetic? Of course, feel free to pause me. If not, let's just get to it. So in this case, here is our molecular orbital diagram. We got our sigma 2s, sigma star 2s, and then right in this case, C and N are going to be adjacent to each other, so we can use the same molecular orbital. In this case, where the pi 2p and the sigma 2p are in this order, and of course the antibonding is always going to be the same, pi star 2p, sigma star 2p. So from here, right, carbon, we got 4 valence electrons. Nitrogen, we have 5. And then we got one more being 10 that's added on because it's an anion. So we're going to have an even number here. So we're just going to fill them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So in this case, we're going to have our 2 electrons in our highest occupied molecular orbital. Okay. So that's just a key term to pay attention to. If you hear or if somebody's asking you, what's the HOMO? That's just basically the highest occupied molecular orbital. In this case, that's going to be sigma 2p. The bond order is going to be your bonding electrons minus your antibonding divided by 2. So in this case, the bonding electrons are going to be 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 electrons in our bonding orbital, right? Basically the ones that don't have a star. Antibonding are the ones that have this little star. So I only have 2 in this case in my sigma star 2s. So 8 minus 2 divided by 2 is going to give me a bond order of 3. So in this case, between C and N, we're going to have a triple bond, which if you do a Lewis structure, we do see a triple bond. Now, is it diamagnetic or paramagnetic? Right, it's going to be diamagnetic, right? It's going to be paired electrons. So everybody, this is heteronuclear diatomic molecules, right? The same stuff as we mentioned with molecular orbital theory, but in this case, we just have 2 different elements, right? Like I mentioned before, if you want to revisit molecular orbital theory, just check out that previous video